So far we have learned how to prepare buffer solutions. We also have learned how to calculate the relationship between the concentration of acid and its conjugate base of a buffer solution at a given pH. What we want to learn now is how much acid does it take to destroy the buffer, or how much a buffer can absorb the addition of a certain amount of acid. That is, to understand the very characteristics of the buffer. So first, let's just observe there's two solutions, both of them created with the same conjugate pair, the bicarbonate and carbonate. All right. So, and notice that both of them have equal concentrations of the equal amounts, therefore equal number of moles of the acid and its conjugate base. So both of them will have the same pH, right? So both of them will have a pH of the pKa that connects these two, which is the second pKa of carbonic acid. So both of these solutions will have a pH of 10 to the 10.3. All right. Now, however, the first solution has a concentration of 0.5 molar of each. The second solution has a concentration of 0.2 molar, one of each. All right. However, so what kind of differences will this lead to? So let's see. Let's start to solve the first question. If we progressively add strong acid to both solutions, what solution will hold the pH for longer? Well, notice that if we add acid, the strong acid that we add will react with the strongest base. Notice that in both cases are bases, right? Bicarbonate could lead to carbonic acid, and carbonate again will lead to bicarbonate. But the acid that we add, the strong acid that we add, will preferably first react with the strongest of the base, which of course is carbonate, right? So notice that if we set up the equation, well, in the first solution, in solution number 1, you have, how much base do you have? You have 0.1 liter times 0.5. This is 0.05 moles. You have 0.05 moles. In the second solution, you have, again, 0.1 liter times 0.2 moles. So you'll have 0.02 moles. So the buffer will be destroyed when you neutralize all of the base. Alright, so notice that in solution 1 it will take 0.05 moles of acid. In solution 2 it will take 0.02 moles of acid. Therefore, solution 1 will hold the pH for longer because it takes more acid to eliminate one member of the buffer solution, of the conjugate. All right. Now, the second question is, what is the pH after adding 0.01 moles of acid? And in this case, let me just, I will first calculate for the first one. We have added 0.01 moles of acid. All right. And so this was initially, at the end, you have, this is the limiting reagent, you have 0.04 moles and 0.01 converted into bicarbonate. Plus, well, of course, we have forgotten to add, we did not do this right, because we have forgotten to add how much of the acid we already had. Well, we already had this 0.05, right? From here, we already had 0.05, so now we have 0.05 that needs to be added to the one created by the addition of acid. Therefore, the pH is pKa. Again, pKa should be 10.3 plus log of the concentration of base, which is 0.04 over volume, and this is concentration of acid, 0.06 over volume. Volume and volume cancel out. All right. This will give you the pH. Now let's do the same for 2. Initially, you have 0.02 moles of base and you add 0.01 moles of base, you also had 0.02 moles of acid. So at the end, this is all gone. What's left is 0.01 moles, and what you have is this much. Alright, so the pH will be 10.3 plus log of, this is the base, 0.01 over the volume, and this is 0.03 over the volume. Alright, now if one puts this into the calculator, you will see that the change in pH in this case will be larger than in this case. In other words, even though the initial pH was the same, because solution 1 can hold the pH for much longer, the solution 1 is a stronger buffer. Also, because for the same amount of acid that is being added, the pH change is smaller. In other words, the solution 1, as we said, is the strongest of the buffer. All right. Just to answer here quickly, how much acid does one need to destroy the weakest buffer? Well, we said that the weakest buffer is solution number 2 because it's the least, the most diluted one, the least concentrated. How much acid does one need to eat? Well, the moment you add in here 0.02, you convert all the acid into, all the base into the acid, and the buffer is destroyed. So for the second solution, if you add 0.02 moles of acid, that will destroy the buffer. On the other hand, for solution number 1, you need to add 0.05. Okay, so it takes longer to destroy. Hopefully that gives some perspective of buffer solutions, because even though in both solutions the pH is the same, they behave differently when you add the same amount of acid or base.